Yes, apart from voltage drop and ambient temperature adjustments, other conditions necessitate using conductors other than 500 kcmil copper for an 800 amp bus duct protected by an 800 amp overcurrent protection device. This is considering parallel conductors in separate conduits. Firstly, skin effect. Skin effect is the phenomenon where alternating current tends to flow near the surface of a conductor rather than uniformly throughout its cross-section. This non-uniform current distribution effectively reduces the conductor's usable cross-sectional area, increasing its resistance and leading to increased voltage drop and heat generation. Skin effect becomes more significant as the frequency of the alternating current increases. At a frequency of 60 Hz, the skin depth in copper is approximately 8.5 mm. This implies that at frequencies exceeding 60 Hz, the effective cross-sectional area of the conductor diminishes, resulting in higher resistance. To mitigate skin effect, a larger conductor size than what would be needed for direct current applications might be necessary. For example, in a 600-volt, 800-amp alternating current bus-duct system, 600 kcmil copper conductors, parallel and separate conduits could be required instead of 500 kcmil copper conductors. Secondly, stray losses. Stray losses encompass energy losses within a bus duct arising from eddy currents and magnetic fields. These losses elevate the bus duct's temperature, potentially causing voltage drop and overheating. Stray losses are more prominent in bus ducts with substantial cross-sectional areas. As an illustration, a 600-volt, 800-amp bus duct with a cross-sectional area of 1000 square millimeters will experience higher stray losses compared to a bus duct with a 500 square millimeter cross-sectional area. To minimize stray losses, it might be advisable to opt for a bus duct with a reduced cross-sectional area. Consequently, for a 600-volt, 800-amp alternating current bus duct, a bus duct with a cross-sectional area of 750 square millimeters could be preferable over one with 1000 square millimeters. Thirdly, continuous rated overcurrent protection device. A continuous rated overcurrent protection device is specifically engineered for applications where the load consistently operates at or near the device's rated capacity. These devices are designed to withstand higher allowable temperature rises than intermittent rated overcurrent protection devices. Employing an 800-amp continuous rated overcurrent protection device in conjunction with a 500 kcmil copper conductor necessitates the application of dirting factors. Dirting reduces the conductor's allowable ampacity, potentially leading to voltage drop and overheating. Therefore, it is advisable to utilize the 600 kcmil copper conductor, parallel and separate conduits for 600-volt, 800-amp bus duct system safeguarded by an 800-amp continuous rated overcurrent protection device. In summary, when determining the appropriate conductor size for an 800-amp bus duct, beyond voltage drop and ambient temperature considerations, factors like skin effect and stray losses must be taken into account. Skin effect increases the conductor's resistance at higher frequencies, potentially necessitating a larger conductor size. Stray losses, arising from eddy currents and magnetic fields, are more significant in bus ducts with larger cross-sectional areas. The use of continuous rated overcurrent protection devices also impacts conductor selection, as dirting factors may be required, potentially necessitating a larger conductor size to maintain adequate ampacity. Comprehensive assessment of these factors is crucial for ensuring safe and reliable operation of the bus duct system. It is crucial to consult the National Electrical Code, or NEC, and other relevant standards and guidelines to ensure compliance with local regulations and industry best practices. These codes provide specific requirements for conductor sizing, overcurrent protection, and other aspects of electrical installations. Engineers and electricians should carefully review these requirements to ensure that the bus duct system is designed and installed in accordance with all applicable standards. Additionally, the manufacturer's specifications for the bus duct and overcurrent protection devices should be closely followed. These specifications provide important information about the equipment's performance characteristics and limitations. Failure to adhere to these specifications can result in equipment damage, system malfunction, or even safety hazards. Furthermore, proper installation techniques are essential for ensuring the long-term reliability of the bus duct system. This includes ensuring that all connections are properly tightened, that the conductors are adequately supported, and that the bus duct is protected from environmental factors such as moisture and corrosion. Regular maintenance and inspection of the bus duct system are also crucial for identifying and addressing potential problems before they lead to more serious issues. This includes checking for signs of overheating, corrosion, or physical damage. Any problems that are identified should be promptly repaired or replaced by qualified personnel. By following these guidelines, engineers and electricians can ensure that the bus duct system is designed, installed, and maintained in a manner that promotes safety, reliability, and long-term performance. It is also important to consider the specific application and operating conditions of the bus duct system. For example, if the bus duct is located in an area with high ambient temperatures, it may be necessary to further derate the conductor and capacity to account for the increased heat. Similarly, if the bus duct is subjected to frequent overloads or short circuits, it may be necessary to use a more robust overcurrent protection device to prevent damage to the system. The selection of appropriate conductors and overcurrent protection devices is a critical aspect of electrical system design. It requires a thorough understanding of the factors that affect conductor ampacity and overcurrent protection device performance. By carefully considering these factors, engineers and electricians can ensure that the electrical system is safe, reliable, and efficient. In addition to the factors discussed above, it is also important to consider the voltage rating of the conductors and overcurrent protection devices. The voltage rating must be equal to or greater than the system voltage. Using conductors or overcurrent protection devices with an inadequate voltage rating can result in equipment failure and safety hazard. Furthermore, it is important to ensure that the conductors are properly insulated. The insulation must be suitable for the operating voltage and environmental conditions. Damaged or inadequate insulation can result in electrical shock hazards and equipment failure. Regular inspection and testing of the insulation is essential for maintaining the safety and reliability of the electrical system. In addition to the National Electrical Code, there are other relevant standards and guidelines that should be consulted when designing and installing bus duct systems. These include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Electrical Manufacturers Association, or NEMA. These standards provide detailed information about the design, testing, and installation of bus duct systems. By following these standards, engineers and electricians can ensure that the bus duct system meets the highest levels of safety and performance. It is also important to stay up to date on the latest developments in bus duct technology. New materials, designs, and installation techniques are constantly being developed. By staying informed about these developments, engineers and electricians can improve the efficiency, reliability, and safety of bus duct systems. In conclusion, the selection of appropriate conductors and overcurrent protection devices for an 800 amp bus duct requires careful consideration of a variety of factors. These factors include voltage drop, ambient temperature, skin effect, stray losses, continuous load requirements, voltage rating, insulation, and applicable standards and guidelines. By carefully considering these factors, engineers and electricians can ensure that the bus duct system is safe, reliable, and efficient. Remember to always consult the latest edition of the National Electrical Code and other relevant standards and guidelines to ensure compliance with local regulations and industry best practices. The NEC is updated every 3 years, so it is important to use the most current version. The NEC provides detailed information about conductor sizing, overcurrent protection, grounding, and other aspects of electrical installations. In addition to the NEC, there are other resources available to help engineers and electricians design and install bus duct systems. These resources include manufacturers' catalogs, technical manuals, and online forums. By utilizing these resources, engineers and electricians can stay informed about the latest developments in bus duct technology and ensure that their installations meet the highest levels of safety and performance. It is also important to note that the design and installation of bus-duct systems should only be performed by qualified personnel. Electrical work can be dangerous, and it is essential to have the proper training and experience to perform the work safely and effectively. Unqualified personnel should never attempt to design or install bus-duct systems. Finally, it is important to remember that safety is always the top priority when working with electrical systems. Always follow all safety precautions and wear appropriate personal protective equipment. Electrical work can be life-threatening, so it is essential to take all necessary precautions to protect yourself and others. The information provided here is for general informational purposes only and should not be considered a substitute for professional engineering advice. Always consult with a qualified engineer before making any decisions about the design or installation of electrical systems. The design and installation of electrical systems is a complex and highly regulated field. It is essential to have the proper training, experience, and knowledge to perform the work safely and effectively. Failure to do so can result in serious injury or death. Therefore, it is always best to err on the side of caution and consult with a qualified professional before undertaking any electrical work. They must also be familiar with local codes and regulations, as these can vary from jurisdiction to jurisdiction. A qualified professional can also help you to select the appropriate equipment and materials for your specific application. This can save you time and money in the long run, and it can also help to ensure that your electrical system is safe and reliable. In addition to consulting with a qualified professional, it is also important to do your own research. There are many resources available online and in libraries that can provide you with information about electrical systems. By doing your own research, you can become more informed about the topic, and you can ask more informed questions when you consult with a qualified professional. The more you know about electrical systems, the better equipped you will be to make informed decisions about your own electrical needs. Ultimately, the goal is to create an electrical system that is safe, reliable, and efficient. By taking the time to do your research and consult with qualified professionals, you can achieve this goal. The specific requirements for conductor sizing and overcurrent protection for an 800 amp bus duct can vary depending on the specific application, the type of bus duct, and the applicable codes and standards. Therefore, it is essential to consult with a qualified electrical engineer or electrician to determine the appropriate requirements for your specific situation. There are several factors that can affect the ampacity of a conductor. These factors include the conductor material, the conductor size, the conductor insulation, the ambient temperature, the number of conductors in a raceway, and the presence of other heat-generating equipment. The National Electrical Code, or NEC, provides tables that list the ampacity of conductors under various conditions. However, it is important to note that these tables are based on certain assumptions, and the actual ampacity of a conductor may be lower than the value listed in the table. For example, the NEC tables assume that the ambient temperature is 30 degrees Celsius. If the ambient temperature is higher than 30 degrees Celsius, the ampacity of the conductor must be derated. The NEC also provides guidelines for derating conductors when there are multiple conductors in a raceway. When there are multiple conductors in a raceway, the heat generated by each conductor can increase the temperature of the other conductors. This can reduce the ampacity of the conductors. The NEC requires that conductors be derated when there are more than 3 current-carrying conductors in a raceway. The amount of derating depends on the number of conductors in the raceway. Overcurrent protection devices are designed to protect electrical circuits from overcurrents. Overcurrents can be caused by short circuits, overloads, or ground faults. Overcurrent protection devices include fuses and circuit breakers. Fuses are one-time devices that melt and interrupt the circuit when an overcurrent occurs. Circuit breakers are reusable devices that trip and interrupt the circuit when an overcurrent occurs. Circuit breakers can be reset after the trip. The NEC requires that overcurrent protection devices be sized to protect the conductors that they are protecting. The overcurrent protection device must be rated to carry at least the ampacity of the conductor, but it cannot be rated higher than the ampacity of the conductor. In addition to protecting the conductors, Overcurrent protection devices also protect electrical equipment from damage due to overcurrents. Overcurrents can damage electrical equipment by overheating the equipment. Overcurrent protection devices can prevent this damage by interrupting the circuit before the equipment is damaged. There are several types of bus ducts available. These include non-segregated phase bus duct, segregated phase bus duct, and isolated phase bus duct. Non-segregated phase bus duct is the most common type of bus duct. In non-segregated phase bus duct, the conductors for each phase are located close together in the same enclosure. Segregated phase bus duct is a type of bus duct in which the conductors for each phase are located in separate compartments. This helps to reduce the risk of phase-to-phase faults. Isolated phase bus duct is a type of bus duct in which the conductors for each phase are completely isolated from each other. This provides the highest level of protection against faults. The type of bus duct that is used will depend on the specific application and the level of protection that is required. Bus ducts are typically used in high current applications such as in power plants, substations, and industrial facilities. They are also used in some commercial buildings. Bus ducts can be used to distribute power to various loads such as motors, transformers, and lighting. Bus ducts offer several advantages over traditional wiring methods. These advantages include higher current carrying capacity, lower voltage drop, and easier installation. Bus ducts can also be more aesthetically pleasing than traditional wiring methods. However, bus ducts also have some disadvantages. These disadvantages include higher cost and more complex maintenance requirements. The decision of whether to use bus duct or traditional wiring methods will depend on the specific application and the cost-benefit analysis. Skin effect is more pronounced at higher frequencies. This is because the higher the frequency, the shallower the skin depth. The skin depth is the distance from the surface of the conductor at which the current density has decreased to 1/E, or approximately 37% of its value at the surface. The skin depth is inversely proportional to the square root of the frequency. Therefore, as the frequency increases, the skin depth decreases. This means that the current is concentrated closer to the surface of the conductor at higher frequencies. This concentration of current at the surface of the conductor increases the effective resistance of the conductor. The increase in resistance is due to the fact that the current is flowing through a smaller cross-sectional area of the conductor. Stray losses are caused by eddy currents and hysteresis losses in the core of the bus duct. Eddy currents are circulating currents that are induced in the core of the bus duct by the alternating magnetic field. Hysteresis losses are caused by the energy that is required to magnetize and demagnetize the core of the bus duct. Stray losses can be reduced by using a core material with low eddy current losses and low hysteresis losses. Continuous rated overcurrent protection devices are designed to carry their rated current continuously without tripping. This is in contrast to intermittent rated overcurrent protection devices, which are designed to carry the rated current for a limited time period. Continuous rated overcurrent protection devices are typically used in applications where the load is continuous or nearly continuous. Examples of such applications include motors, transformers, and lighting. Intermittent rated overcurrent protection devices are typically used in applications where the load is intermittent or cyclical. Examples of such applications include welders, compressors, and pumps. The choice of whether to use a continuous rated or intermittent rated overcurrent protection device will depend on the specific application. The NEC requires that the overcurrent protection device be sized to protect the conductors that it is protecting. The overcurrent protection device must be rated to carry at least the ampacity of the conductor, but it cannot be rated higher than the ampacity of the conductor. In addition, the NEC requires that the overcurrent protection device be able to interrupt the fault current that is available at the point of application. The fault current is the current that will flow during a short circuit or ground fault. The fault current can be very high, so it is important to use an overcurrent protection device that is able to interrupt this current safely.